So this is 7.3.3 electric potential. So we define electric potential in a very similar way to the gravitational potential, in that it's the work done to bring a unit positive charge to that point from a place of zero potential. So the key difference is that it's the work done per unit positive charge to bring it there, because positive charge is our test charge. So this is the work done per unit positive charge to bring it to that point from a place of zero potential. Which is infinitely far away. And put a box around that definition. It's a definition you need to know. So what we'll do is we'll sketch a radial field again. So you've got a negative charge. And since it's a negative charge, our field lines point towards the charge, because a positive test charge would experience a force that goes in. Then I'm going to sketch a couple of equipotentials. So I'll sketch one there, and I'll sketch one on the outside. So we can call the one on the inside minus 50 volts, and on the outside minus 10 volts. And if we want a positive charge, I'll call that plus Q, to go from that point or that equipotential to the inner equipotential here. Some work will be done. But in this case, again, because it's a positive charge in a field that's generated by a negative charge, our test charge is not going to be doing the work, rather its work is going to be done on it. So just like before, the work done is equal to the charge multiplied by the potential difference. And similarly to before, the potential at a point is given by Q over 4 pi epsilon naught r. And the Q in this equation is the one that's creating the field, not the one that's experiencing the force in that field. So this is the charge creating the field. So we can evaluate it for this scenario. We ignore the positive charge that we have in there. Instead, what we're going to do is we're going to look at the potential first and why it's negative. So if we look at the equation for the potential at a point, it's created by a negative charge. That means that this value of Q is going to be negative. So in that case, it gives us a negative number, similar to how in gravitational fields we have a negative number. Yeah? But if it was being generated by a positive field, then this value of V is going to give us a positive number because Q would be positive. So the value of V is going to depend on, or the sign of V I should say, depends on whether the charge that's creating the field is positive or negative. And that's going to determine whether work has to be done on a positive charge or work is going to be done by the positive charge. This equation then links to the second equation. And here I'm going to make a note that this value of Q is the charge experiencing the field. Or charge experiencing a force in the field. Either way, it's fine. And then we can see that if we have negative V here, then the work done also depends on the sign of the second value of Q. So whether you have a positive and a negative charge, or a negative and a positive, or two positives or two negatives, that's going to affect your value of whether work is being done on or by the charge. So you have to think carefully about it this time. It's not as simple as it was in gravitational fields, because now you can have positive and negative charges. In gravitational fields that wasn't the case. You could only have positive gravitational charges, which is just mass. You can't have negative mass, right? But the relationship between the potential and separation still remains, where potential is proportional to 1 over r. So the relationship, when you graph it, still remains the same. So if I put V and R, we still get a 1 over R graph. And the electric field strength is still dV dr. And if we evaluated that, if we did dV dr, what we end up with is that E equals to Q over 4 pi epsilon naught r squared, but we also get a negative sign that appears as well. If we were to ignore the negative sign, so we only look at the magnitude, we get that the magnitude of E is equal to Q over 4 pi epsilon naught r squared. This here can also be written as, because Q over 4 pi epsilon naught r is equal to V, so we've got minus V over R. Now if we were to graph that, we would basically have to extend this line down. And then I would put E on this side, because it's over r squared, it's going to fall a lot quicker than it did with v. Now we can look at a uniform field. If we look at a uniform field, where we've got two plates, we charge one of the plates to positive 1,500 volts, and the other plate is at 0 volts. We've got field lines equidistant apart. And then we could draw equipotentials in there as well. Now the equipotentials are also going to be equidistant apart. And your potential is going to change linearly this time rather than radially. So what I mean by that is if you're exactly halfway between your plates, you're going to have exactly half the potential difference. So from 1,500 volts to the center between the plates, which would be over here, you would have 750 volts. So it changes linearly with the separation of the plates. So if we were to graph that, and we put R here and V there, we would get a linear line. But if we look at the electric field strength inside the plates, what do you notice about the electric field strength by looking at those field lines? It's always the same. The lines neither get closer together, nor do they get further apart, which basically means the field strength inside the plates is always the same. So in this case, the field strength is just a constant line within those plates. And then what we can mark over here as a limit to this graph, which is D, where we get the separation of the plates. So that is D. Outside of that, we don't have an electric field. Now, the uniform field actually does have some non-uniformity to it as well. So in actual fact, some of the field lines do come out of those plates. So I'm going to show you that just to make sure that you recognize it. In the event, it's a rare event, but sometimes we do see examples of where we have field lines outside. So another example, plus 4,000 volts and 0 volts. So we do our usual with the field lines, drawing them approximately equidistant. And then what happens is on the edges, we get a curved line here and a curved line here. And then right on the outside, we get a funny shape like this. So our equipotentials, the easiest one is that one that goes through the center. It's just a straight line. So if we went from 4,000 volts to 0 volts, halfway in between has to be 2,000. Then halfway between the 2,000 volts and the 4,000 volts, we get a line that comes in like this. Now notice the equipotential is always perpendicular to each of the field lines. That's why it curves on the edges to consistently be perpendicular with each of the field lines. So this equipotential is going to be 3,000 volts. And then likewise, halfway between the 2,000 volts and the 0 volt plate, I've tried to keep it as perpendicular as possible, but I did have some wobble while drawing it, so that will be 1,000 volts. And then the equation that's linking the gravitational field strength to the potential is E equals to V over D. So this is the potential difference between plates. And D is a separation of the plates. Now notice it's not about where you're located. So you might have a proton that's located between the plates, but D is not where the proton will be located. It's the separation between the two plates. And then V is not the potential at which that proton is at. It's about the potential difference between the plates. Now, if you did it about the location, then you have to do it for both of them. So, for example, if you had a proton that was flying halfway between the plates, the potential would then be half, wouldn't it? Right?
Yeah.
And if the potential is half, but you're halfway between the plates, your separation is also half. And the two halves will cancel. So you still have a constant gravitational field strength, whichever way you do it. But the best way to do it is to evaluate it about the plates before you start looking at the location of your charged particle between the plates. All right, let's do an example. This is called the pith ball question. So we have two plates, and within the plates we have a ball attached in a string. The ball has a mass of 1.5 grams. This angle is 50 degrees. And it's got a separation from its equilibrium position of 7.6 centimeters. And the separation between these plates is 20 centimeters. So the question will ask you, A, to draw a free body diagram of the ball. Part B is to find tension. Part C, to calculate the electrostatic force. on the ball. And part D, if the plate potential difference is 3 kilovolts, what is the charge of the ball? You can pause the video here to answer the questions and then replay the video when you're ready to see the working out. Okay, so let's begin with part A. So the question says to draw a free body diagram of the ball. So what we're going to do is we're going to draw the ball and all forces that act on the ball. So here's our ball. Now we know that the ball is attached to a string, and for some reason the string has been displaced towards the right. Under normal conditions, without those charged plates, we know that the ball would just remain undisplaced on the string. So the fact that there's a displacement towards the right means that there is an electrostatic force or some force acting towards the right. And there's no way else a force is going to be acting on that ball other than electrostatic force in this situation. So we know that there will be an electrostatic force to the right, and we'll label that as Fe. We know that the ball has mass, and if it has a mass, then it has weight. So we know that going down, we've got mg. But the ball has been displaced towards the right, but it's not currently in motion. And we know that it's on a string, and the string is fixed at some point. So there must be tension on that string, which counteracts the electrostatic force and the weight to keep it in position. So tension will be acting at 50 degrees, and it will be that way. So that's the answer to part A. Part B asks us to find the tension. So to find tension, what we need to do is we need to consider what components are actually balancing whichever force. So right now we don't know what the electrostatic force is, but we can very easily work out what mg is. Mg acts vertically down. A component of tension acts vertically up. So if we draw a triangle of tension like this, we've got Fe acting horizontally, and we've got mg acting vertically down with 50 degrees between them. So straight away, we can make an equation here by considering that it's a right angle triangle. And we know that T cos 50 is equal to mg. So we can simply rearrange this equation to find T. So T is equal to mg over cos 50. M was 1.5 grams. So 1.5 times 10 to the minus 3 times by 9.81 all over cos 50. And that should give us a very small force. What is it? Is it like 2.3? 0.0T. So 2.3 times 10 What is it?
-2. What is it? -2?
Write it in standard form. -2. Now, for the next part, we can work it out in many ways. So, one of the ways is, you know it's a right angle triangle, so you can either use Pythagoras to work it out, where you do t squared minus mg squared equals to fe squared. Or, since you know t, you can use the sine rule as well. So you could say that t sine 50 is equal to fe. Any of those ways will work out part C. So I'm going to opt to use sine. So we say that t sine 50 equals to fe. And we know that t is 2.3 times 10 to the minus 2 times by sine 50 equals to fe. So fe is equal to 1.8 times 10 to the minus 2 newtons. And then finally for part D, we said if the plate had a potential difference of 3 kilovolts, what is the charge of the ball? So now that we know the electrostatic force, we can relate it to equations. So we know that for a uniform field, we've got F is equal to EQ. And we also know that E is equal to V over D. Because we don't know what the electric field strength is, but we have been given a potential difference between the plates. And we have been given a separation of the plates. So we're going to put these equations together, make a substitution. So we've got F is equal to QV over D. And now we're going to rearrange to get Q. So Q is equal to F times D over V. We know that F of E from the previous question is 1.8 times 10 to the minus 2. The separation was 20 centimeters, so that's 20 times 10 to the minus 2. All over potential difference, which is given as 3 kilovolts, so that's 3 times 10 to the 3. And when you put all of those together, we get a charge of 12, or 1.2 times 10 to the minus 6 coulombs. Now, we don't know whether this charge is positive or negative. All we know is its magnitude, because we don't know which plate was positive and which plate was negative. The only thing we know is that the potential difference between the plates. And that is the end of 7.3.3.